moving on. Let's talk about acceleration for just a second. So this is the instantaneous velocity of the object is the speed of the object with a direction, because we're talking about velocity here. So number 1 says accelerating objects that are objects that are changing their velocity. Name 3 controls on an automobile that causes it to accelerate. So a couple of them. Brake pedal is one that will make it to accelerate. Now, you're like, wait a minute, Ms. Smith, a brake doesn't make you speed up. Okay, acceleration is not necessarily speeding up. You could have what's called negative acceleration, which is slowing down, which could be done with your brake. Deceleration is not a real word. That is not a real concept in physics. So that's actually bad language if you say decelerating or deceleration. It's called negative acceleration. The gas, of course, to speed up. Another one would be a steering wheel. Okay? Now, you may not necessarily change how fast you're going if you turn the wheel, but what's happening, let's say that you have the cruise control set and you're set it at, I don't know, 50 miles an hour, and you turn your wheel to the right, even though your velocity is constant, because you've got it on cruise control, because you are changing direction when you turn that steering wheel, you are technically still accelerating because your direction is changing. All right. Number 2, an object is accelerating if it is moving, so circle all that apply, if it is moving with a changing speed or it is in a circle. Now, B, moving extremely fast doesn't necessarily mean that you're accelerating. If you're moving extremely fast, that could be a constant velocity. If you have a constant velocity and you're not changing your direction, you're not accelerating. That's not happening. Okay, E says downward. Well, okay, that makes no sense at all, because remember, the acceleration is a rate, how your velocity is changing over a period of time. E makes no sense. C, with a constant velocity. Again, you got to have a change in velocity to have acceleration in the first place. And then F doesn't work because we both have A and D. All right, 3, if an object is not accelerating, then one knows for sure that it is at rest, moving at a constant speed, slowing down, or maintaining constant velocity. So it's going to be either one of these, moving with a constant speed or maintaining constant velocity. So you're like, well, wait a minute, Ms. Smith, what about A and C? Okay, accelerating objects that are changing their velocity. A velocity is a speed with a direction. An object with changing velocity can be changing its speed and or changing its direction. Okay, so there you go. Now, just because something is slowing down, when something is slowing down, that means that you are accelerating, because we're looking at things that are not accelerating. I mean, if you're at rest, then you're not accelerating at all because you're not moving. All right, number 4. An object with an acceleration of 10 meters per second squared will, let's see, move 10 meters in 1 second, move 100 meters in 10 seconds, changes velocity by 10 meters per second in 1 second, or D, have a velocity of 100 meters per second after 10 seconds. Okay, the only one that makes any kind of sense is B. Okay, because it says changes velocity by 10 meters per second in 1 second. That's correct, because acceleration isn't how far are you moving in a certain amount of time. That's not what acceleration is. That's velocity. Acceleration is the rate at which you are increasing or decreasing. Okay, so if this says you're moving 10 meters per second in 1 second, that is a rate over a time period, which is exactly what acceleration is. All right, number 5. Amma speeding puts the pedal to the metal and increases her speed as follows. 0 miles per hour at 0 seconds. So we're at 0, 0 here. So 0 miles per hour over 0 seconds. Okay, at 1 second, she's at 10 miles per hour. At 2 seconds, she's at 20 miles per hour. And at 3 seconds, she's at 30 miles per hour. So I'm hoping that you're seeing a pattern here. Okay, so it says, what is the acceleration of Ima's car? So I'm hoping that you would see a pattern. So for every second, you're increasing your velocity by 10 miles per hour. Now, sometimes you're not given all of this data. Sometimes all you're given is the beginning velocity, so v sub I, which would be 0 miles per hour, so that's the initial velocity, and then you would be given v sub f, which is final velocity, and that is 30 miles per hour, and then you would be given that at total time, her change in time is excuse me, we ended on 40. I'm sorry, I forgot about 40 over there, so 40 over there. So that would be the end here, and it took her 4 seconds to do that. So you would literally go 40 minus 0 divided by 4. Well, that equals 10. Okay, well before, when we mapped it all out, it was increasing 10 miles per hour per second. So how you would write that is you are increasing 10 miles per hour per second, okay? Because when I did this, when I did 40 minus 0, that was miles per hour. And on the bottom, you had a double ratio here. That was 4 seconds. So 10 miles per hour per second. Now, had this been in meters per second instead of miles per hour, then it would have been meters per second, or meters per second squared. All right, number 6. Mr. Henderson's imaginary Porsche accelerates from 0 to 60 in 4 seconds. Its acceleration is, all right, so let's identify what we've got here. Erase a little bit of this. Let's identify what we've got. So I'm going to zoom in a little bit. So 0, it's going to be your v sub I. And then your 60 is going to be your v sub f. And this is your change in time. So you literally, all you have to do is put in the formula. So because you know acceleration is v sub f minus v sub I over your change in time. So v sub f is 60 minus v sub I, which is 0, divided by the 4 seconds to do that. 60 minus 0 is 60. 60 divided by 4 is 15. Okay, so let's look at the answers that we've got. Okay, so we've got 60 miles per hour. No, not even close. We've got 15 meters per second. Okay, yeah, maybe. Let's check the other ones first. 15 miles per hour per second. Ooh, I didn't look at the units. Maybe. We'll see. Negative 15 miles per hour per second, or E, none of these. Okay, so we know that it was 15. So let's check our units real quick. I'm going to do the units in a different color. We knew that initial velocity, that the units were 0 miles per hour. And we also knew that it was 60 miles per hour here, and you subtracted those two. On the bottom, it took 4 seconds. So when you subtracted these, you got 60 miles per hour over 4 seconds. You did that math there, and you got 15 miles, that's 4 seconds, 15 miles per hour per second. So the answer is this one here. It is C, 15 miles per hour per second. Now, you're like, wait a minute, Ms. Smith, could it have been the negative? Yes. Had the car started at 60 and slowed down to 0, like slammed on the brakes and went from 60 to 0 in 4 seconds, then it would have been negative 15, okay? Because then these two would have been flipped, and it would have been 0 minus 60. There's where you would get your negative number for negative acceleration. Okay, moving on. That was the correct answer for that one. All right, number 8, a car slows down from 32 to 8. Now you notice how these guys have got plus signs there. That is direction. Okay, remember, a negative can mean direction. Also, if you have a plus sign in front of it, it also can mean direction. It means positive x direction is what that is meaning. All right, so he said we went from 32 meters per second, so that is going to be v sub f, excuse me, backwards, v sub I, that's where we started at. And then 8 meters per second is going to be where we ended at, so that's v sub f. So let's do the formula. V sub f minus v sub I divided by change in time. Okay, so v sub f is 8 minus 32. Notice I didn't put the plus signs in there because I'm not really worried about direction at this point. And then I over 4. Now let's do units. Let's do units in different color. Meters per second. Meters per second. And this is in seconds. So 8 minus 32 is 24 divided by 4. Let's put the units in here. This is meters per second. This is 4 seconds. 24 divided by 4 is 6. Let's look at the units for just a second. This is going to be meters. Oh, wrong color. Meters per second per second. Now, I'm hoping at this point that you screamed the screen just for a little bit and realized that I forgot a negative. I sure hope that you did. Now watch what I messed up here. This here, when you did this, 8 minus 32 gives you a negative 24. So that negative needs to go there. So negative 24 divided by 4 comes out to be negative 6. Now before we were talking about how we had our positive direction here. Well, this is negative acceleration. So technically your direction is in the negative x direction because you are slowing down. Okay, and you can see this when we do talk about particle models. All right, so the answer is going to be negative 6 meters per second squared. All right, let's see what we got here. Car is moving eastward along Lake Avenue and increasing its speed from 25 to 45. All right, so we're going from 25 to 45, so that means positive acceleration. So that means that our direction of our acceleration is eastward. Okay, because when we are going in the positive, when we have a positive acceleration, your x direction is equal to your acceleration direction. Okay, so this is when we have positive acceleration. Let me draw this a little smaller. Okay, if you have positive acceleration, then your x is in the same direction, x direction is in the same direction as the acceleration direction. Now what I don't mean like literal acceleration direction, that's not what I'm talking about. What I mean is the motion of your acceleration. Are you headed to the left? Are you headed to the right? Are you up, down, east, west, whatever it is? That's what I'm talking about. If you have a negative acceleration, your x direction is opposite of your acceleration. So I guess I'll go back and I'll write this a little bit better. So your x direction is the same direction as your acceleration. And this is in the opposite direction. Oh, goodness. For your acceleration. All right, now this particular concept is really hard for a lot of you to grasp, so I'm hoping that me writing this out like this is helping. So let's try a couple of these problems. It says a northbound car skids to a stop to avoid a reckless driver. So that means we're slowing down, so we have a negative acceleration, which means that our direction of the acceleration is southbound or southward because it was north. But because we have negative acceleration, the direction of the acceleration is southward. All right. So the Olympic diver slows down. So we have negative acceleration. Olympic diver slows down after splashing on the water. So splashing down, here's your direction right there, down. So it would be upward. Okay, a southward bound. So here's southward. Is delivered by an opposing team, slowed down and stopped the goalie. So it's slowed down, so it's negative acceleration. So we're saying the opposite of the direction it was going, which would be northward. Okay, a downward falling parachute pulls the cord and rapidly slows down. So negative acceleration. So we're going to say upward. Which makes sense because if you think about it in movies, when somebody jumps out of a plane and they open their parachute, they all of a sudden just fly up in the air. Okay? The reason why that works is a whole other concept we'll talk about next unit. But that's because you had that negative acceleration. You were slowing down. So it looked like you were headed upward. Okay, anyway, moving on. A rightward moving Hot Wheel car slows to a stop, so negative acceleration. So this is going to be leftward. Okay, a falling bungee jumper slows down as it nears the concrete sidewalk below. So falling, that just means that they're going downward, and we're slowing down, so that means negative acceleration, so that's upward. Okay, next. All right. I actually really hate this question. I really do not like it. So we're just gonna skip this. It's just a really terrible question. Just because of how this is viewed, it gets really confusing. Just because this is a terrible picture to use as a reference, so we're just skip that. All right, moving on. Okay, these are some of my favorite. I love these so very much. You will have to draw a particle diagram on your exam, so please be prepared to do this. All right. Motion diagrams for an amusement park ride are shown. The diagrams indicate the position of the car at regular time intervals. For each of these diagrams, indicate whether the car is accelerating or moving with constant velocity. If accelerating, indicate the direction, right or left, of the acceleration. Support your answer with reasoning. All right. So, question is, this on A, we notice that the distance between the cars is the same. So that means we are not accelerating. Technically, it's at a constant velocity. Because distance between cars are the same. Okay, now since we don't have acceleration going on, then we don't have a direction, so we're just not going to put anything there. All right, next one. Spacing between cars increases. If you see this, the spacing between the cars increases. So that means that we have acceleration. And because it's increasing, we're going to the right. Okay? For all of these scenarios, this is point 0. This is your starting point. For every single one of these scenarios, this is point 0. Like your origin. Okay? So everything to the right of this point 0 here is technically that's the origin. Everything to the right will be in the positive x direction. Okay, this here. It looks like they are all the same distance between them. Now the difference between A and C, even though they both have the same distance between all of the cars, C is faster because that distance between them is shorter. Okay, so we're going to say same distance between cars. Okay, so we have no acceleration here and there. Okay. Oh, so direction is this way. I forgot to list the direction of the acceleration. We're going to say right because it is speeding up. Because we have a positive acceleration, the direction is the same way as the acceleration. Okay, next. We have increasing space between cars. Okay, so that means we have no acceleration. Oh, excuse me. Got ahead of myself. That means we do have acceleration. Yes. Okay, and because we are increasing, that means positive acceleration, which means direction. And positive acceleration means direction, acceleration, direction are in the same direction. So we're going to say to the right. All right, the next one. We have decreasing space between cars. So that means we are slowing down. So that means, yes, we have acceleration. So decreasing space between cars. Okay, so that means that we are slowing down. So yes, we have acceleration, but remember the x direction, the actual direction of the car is this way, but the direction of the acceleration is what's different. Okay, so the direction of the acceleration will be to the left because you're slowing down. All right, we're going to skip this one. Not important at this point. All right, let's look at number 3. It says, based on the oil drop pattern of car A and car B, which of the following statements are true? Circle all that apply. So you look at car A and car B. So it says both cars have a constant velocity. Well, that's not true because they would be evenly spaced. So I'm going to cross that one out. Nope, nope. B, both cars have an accelerated motion. Yes, that's true because you have the space increases as you go to the right. So these cars are going to be going to the right. So their space increases. So yes, that is one of them. Let's see what else. Car A is accelerating, car B is not. Nope, not true. They are both accelerating. Car B is accelerating, car A is not. Nope, that's not true. E, car A has a greater acceleration than car B. Okay. So car A has a greater acceleration than car B. Yes, that's correct. The reason why I know that are because of these two dots here on both of them. These are further apart on car A than they are on car B, which means that this one is moving faster. Car A is moving faster. And so since I know car A is moving faster, that means that F is not correct. Number 4, an object is moving from left to right. So we're going, an object is moving from left to right. So that's going to be your positive x direction. Its motion is represented by the oil drop diagram below. This object has a blank velocity and a blank acceleration. The velocity of an object is always in the direction that it moves, in this case to the left. If an object is slowing down, as is in the case here, then its acceleration is opposite of the direction motion. Okay, so this car is, so object is moving from right to left, excuse me. Right to left. So the car is moving this way. So we start out with some big spaces between the dots and then they get a little bit smaller and smaller, smaller spaces. So that means that this car is slowing down. Okay, so we know that its velocity is always the same direction as the car is moving. So we know the car is moving to the left. So that means that our velocity is to the left. So A is out, E is out, B is out, and F is out. Okay, so we're left with C or D because our velocity direction is always the same direction as the car is moving, and we know the car is moving to the left because that's what the problem says. And plus we've got this little arrow right here. Now because we are slowing down, the direction of the acceleration will be opposite of the direction the car is actually going. So the only one that does that is C. All right. Renata Oil's car has an oil leak and leaves a trace of oil drops on the street as she drives through Glenview. A study of Glenview's streets revealed the following traces. Match the trace with the verbal descriptions given below. For each match, verify your reasoning. All right, so we've got A, B, and C. All right, so here's the first one. Let's do this one first. It says, Renata was driving with a slow, constant speed, decelerated to rest, remained at rest for 30 seconds, then drove very, very slowly at a constant speed. Okay, so the only one that makes any kind of sense for that one is going to be C. Now let's talk about why. So this spot here is a constant speed. Okay, and then right there, because they're all bunched up, they're slowing down. They're all bunched up and they're increasingly getting close together. That means they're slowing down. And then this means that they stopped for a while. Talked about how that big black spot is when they stopped. This part right here, they're evenly spaced and they're close together. So that means slow, constant speed. All right, so there's your explanation. I'm not going to write it in the reasoning blank because I'm drawing on the diagrams a lot better anyway. All right. The second one, Renata rapidly decelerated from a high speed. Okay, first off, I hate this. We just talked about how this is not a real word. Deceleration is not a real word. Okay, it should say negative acceleration or slowing down. So Renata rapidly slowed down from a high speed to a rest position and then slowly accelerated to a moderate speed. Well, we've only got 2 left, okay? And we know that when they stop, it's going to leave a large black spot. So diagram A is the only one that it could be because we already said the diagram C. Now, let's look at a little bit closer. Here, they're spaced out. There's a whole lot of space between here, so that means they're moving fast. And then they slowly start decreasing the distance between them until it stops. So this is slowing down. And then we stop here. And then we slowly increase. Accelerate with a moderate speed. Accelerate with moderate speed. Okay. Number 3, Renata was driving at a moderate speed and slowly accelerated. So here we go. It is B, moderate speed. They're, spaced together, not too large, not too small. So a moderate speed. And then they increasingly get larger. So that's accelerating.